Okay. Hello and welcome to the third Grid Talk of the 2017 series. Today I'm thrilled to introduce Dr. Tim Sherwood. Dr. Sherwood is a professor of computer science at UC Santa Barbara, specializing in the development of high-performance, low-powered, and mathematically verifiable computer systems. He holds a Bachelor's of Science degree from UC Davis, Master's and PhD degrees in Computer Science and Engineering from UC San Diego, and now serves as the Associate Vice Chancellor for Research for UC Santa Barbara. He is a distinguished scientist of the ACM, co-founder of a startup on computer hardware security, winner of the UCSB Academic Senate Teaching Award, and 7-time recipient of the Top Pick Award from IEEE Micro Magazine for contributions related to chip and silicon systems design. Today, he's going to tell us how he tricked a rock into thinking. So please help me welcome to the stage, Dr. Tim Sherwood.
Hi. Hi, it's wonderful to see you all here. I wanted to start today's talk with just a very brief point in history, because something pretty amazing happened about 20 years ago. Around 1996, Garry Kasparov played Deep Blue. And Deep Blue, at the time, was one of the 300 most powerful supercomputers that existed in the world. And Garry Kasparov lost a game to this supercomputer. And this is actually a pretty remarkable thing. This is the first time ever a sitting world champion had lost a game to a computer. And I think that's actually a pretty remarkable feat. For one, I think also it's pretty remarkable that I think many of the people in this room may have not been born then, and also may think that's actually not very remarkable, because they know computers are so powerful and so fast, of course a computer is faster. And in fact, your intuition is absolutely right. The mobile phone that you have in your pocket, assuming you've bought one in the last couple of years, is actually far, far more powerful than the Deep Blue supercomputer. In fact, running the right software, your cell phone could beat, with very high probability, many of the best chess players in the world today. It's pretty amazing. It's also pretty remarkable that 20 years before this happened, a leading expert in the world, someone who deeply understood chess and actually has written books on both chess and computers, said that the idea of an electronic world champion belongs only in the pages of a science fiction book. This is pretty amazing. These are actually all three pretty remarkable chain of events that's happened over the last 40 years. We went from something which was strictly in the realm of science fiction to something which is at the limit of what we could do if we marshaled all of the resources that we had at our disposal and put them into a single task, to the mundane, things that we just take for granted in our day-to-day life. And this is actually a pretty remarkable transformation that's happened over the past 40 years. And I think sometimes something that we often lose sight of, we just assume the next amazing thing is happening, and we very quickly pull it into what we consider normal. But I think there's so many young people here today who are just beginning on their career. I ask you to think, where are you going to be in your career 20 years from now? Where are you going to be in your career 40 years from now? Probably still very active in your field. And the things that are science fiction now may become mundane by the time you're finished. So you're preparing now to embark on a career of significant transformation. So this is not just about chess. This is not talk about chess in any way. But actually this happens again and again. Voice recognition was a technology which was seen by many to be just completely not feasible, that you'd have to fully understand the way a human being communicated in order to do text recognition. And of course now, this is just something we take for granted, that you can do voice recognition when you send a text message. The same could be said of driving cars. We're maybe not as far along there, but in 2005, we started really pulling together huge amounts of computational resources to see if we could build a self-driving car. And they looked nothing like a little car that you would buy at the store. They looked like this, huge behemoths that used all kinds of incredibly expensive equipment. And it wasn't 20 years before this that I remember people talking about this idea of a self-driving car and just laughing that it was not a realistic idea to pursue. And now, 15 years from now, I fully expect this to be just mundane, and for us to have amusing anecdotes that we share with our family about falling asleep in the car and telling it to go to one city to Vancouver, Canada, and waking up in Vancouver, Oregon somewhere. These are the kinds of stories that I fully expect to happen in 15 years. So what's driven this huge transformation in what's been possible? Well, I would argue a huge piece of it is actually computing. So as I said, the cell phone in your pocket is probably about 50 times more powerful than the Deep Blue supercomputer. Again, one of the 300 fastest supercomputers in the world at the time. And that machine was about 50 times faster than the machines that were available in 1973 when this individual said that, electronic world champion belongs in science fiction. And this is a huge transformation. In fact, if you go back and you said, oh, if I was trying to buy all the computation that's available on my cell phone today, but buy it in 1973, it would cost you about somewhere on the order of $300 billion, right? That's how much computation has changed. From something that would have cost you $300 billion to something you could buy at the store, and you carry it in your pocket and you get mad when it gets chipped, right? That's how far we've gone in 40 years, which is pretty amazing. So you're all 1973 billionaires and you didn't even know it. Okay, so there's a couple of big ideas that I hope you take away from this talk. And this first big idea is that for computing, the gap between what's science fiction and science fact is actually a lot closer than you might think, because we've been just improving exponentially, and that it's hard to imagine. So for the second part of the talk, I want to try to start to break down why that might be. How is it possible that we've been able to achieve this, magnificent improvement in performance? So let's start with just a simple cell phone, and let's take it apart, and let's look what's going on inside it. If you take your cell phone, if you blow it apart like this, I do not recommend you do this. If you want to keep your cell phone, you get your display and your battery, and then actually, if you kind of zoom in right here, you can actually see this little strip down the middle, which actually contains all the computing power of your cell phone. In fact, this little square right in the middle is actually the main guts that make it all work. That's your microprocessor right in the center. Okay, and inside that little package is actually this little chunk of silicon, which gets all this work done, an amazing amount of work done. I think this quote actually captures so beautifully what I love about my field of computer architecture. If you ever code something that feels like a hack but it just works, just remember that a CPU is literally a rock that we tricked into thinking. So this Ben Driscoll came up with this quote on Twitter. He also has an amazing webcomic. You should check it out. But this quote actually just so perfectly captures me the amazement that I feel every day in my job as I build faster and faster microprocessors. We take this monocrystalline single silicon ingot and slice it up into these very thin chunks, and then we grow this circuitry right onto the surface of that piece of silicon, and then we put electricity on it, and it does amazing things, absolutely amazing things. And sometimes it's easy to forget that. So, how does this actually work? How is it actually possible to build a microprocessor? Well, really, it's both incredibly complex and incredibly simple at the same time. So, at a high level, really, a microprocessor is really made of two things: switches and wires. Those are really the only two bits. Okay, and the switches, we can make them really tiny and really fast. I'll give you some sense of how tiny and how fast. And the wires are actually what connects them all together, and actually how we decide to wire these up is actually an incredibly interesting part of this, which I'll talk about in a little bit. Okay, so many people have maybe heard the word transistor, and maybe you've even seen transistors at some point in the past, but look, at a high level, really, in a microprocessor, a transistor acts as a switch. That's all it does, for the most part. It can be in one of two states. It can either be open, in which case it acts like it's just disconnected, or it can be closed, in which case now it acts like a wire. And that's basically the two states. So just like any switch, you can open and close it all the time, and it does switch things. That's it. So the neat thing about this is, rather than actually have to have a tiny person who actually pulls these switches up and down a billion times a second, in fact, the switches are actually what controls the switches? Other switches. So we can have electrically controlled switches. And those switches basically, again, on or off. And that's it. That's basically what you need to know about transistors in order to make a microprocessor. And a chip full of these transistors is no more a computer than your brain is a bag of neurons, right? Of course, if I just handed you a bag of neurons and said, this is my friend John, right? That's not good, right? First, how did I get this bag of neurons? It's many questions are asked. But instead, what makes it interesting is actually how they're all connected up. That's where the most interesting piece lies, in my opinion. And the same is true of a microprocessor. How you actually take these tiny switches and connect them up in new and interesting and innovative ways is what is a big part of what drives our field forward. So you could take these tiny switches and you could build all kinds of amazing stuff. So, but they get really complicated really fast. So here's a picture. This is actually should be a somewhat valid circuit diagram of a 1-bit adder. Okay, this adds two 1-bit numbers, which are either 0 or 1, right? And then 0 plus 1 is 1, and 0 plus 0 is 0, and all those good things happen. And you have to work it out exactly what happens when the different switches are in the different cases. And you put your input A and your input B on there, and then either on or off basically propagates to the output. One of the things I love about this is there's nothing magical in here. You can break it down at each little step, and we figure out how to build a switch, and then we take that switch, and then we figure out how to build a 1-bit adder, and then we take that 1-bit adder, and then we figure out how to build a multi-bit adder, something that can add numbers like you and I might think about them. And then we might take that multi-bit adder and then build something that does, more complicated math, like does multiplies on using the adder, because you use addition to do multiplication. And then you might take that multiplication and build multiple of them and build something that does matrix multiplication. And you might take those things and then put them together and call that, hook it up with a bunch of wiring and call that a microprocessor. And in each step you build complexity, you build functionality on top of, one thing on top of the next, building. Well, these transistors, the story of transistors is actually really interesting because now not only can we build these switches, but we could build a lot of them. Okay, I would argue a mind-blowing amount of them. All right, so in the 1950s, we really only knew how to build one. We could build one at a time, And then sometime in the 1960s, we started saying, hey, look, actually, since I already have the silicon here, and I'm already putting transistors on it, rather than just put one, why don't I put 4? And that's a good idea. We should do that. That's way cheaper. Let's put 4 on there. And so in the 1960s, we did. We started putting 4 on there. And that was pretty good technology. We managed to go to the moon using that technology. But we were limited to on the order of 16 transistors. By the 1970s, we could actually start to put enough transistors on a single chip that we could actually start to build stuff that would run software, right? So we could actually start to build our microprocessors. So we had these little 8-bit CPUs. So we're dealing with thousands of transistors at this point. And then in the 80s, we're starting to do, 250,000 transistors. Okay, by the 90s, we're doing 3 million transistors. And we're building really huge, complicated microprocessors that do all kinds of stuff that, they take your software and it analyzes it and it tries to run the software in an order that's different than the way that you wrote it to run to make it go faster. All kinds of really interesting tricks like this. And by the 2000s, we were actually saying, we could do all that stuff, and we can actually take multiple of those processors and stick them all on the same chip. And then we have multiprocessors, and then we're doing 500 million transistors. And today, now we're building whole systems on chips. So we have so modern, a modern cell phone chip actually has multiple multiprocessors on it. Okay, so it has a multiprocessor over here that does all your runs your Angry Birds, and then it's got another chunk over here that runs all your GPU stuff, and it's got another chunk over here that runs all the cellular modem that talks to the radio, and you have all these different multiprocessors there. And then by the so at this point we're doing close to 2.5 billion transistors. In fact, I just looked it up preparing for this talk. I think the biggest one design I could find, the commercial design, is 4 billion transistors. And this trend is exponential in a real way. I mean, it keeps doubling here, if you notice these numbers, right? And if you extrapolate, by the 2020s, we should be building something with 100 billion transistors, and I say 100, that's ridiculous. I don't know what 100 billion transistors machine would look like, but yet we will build it. What it looks like, it remains an open question, actually. How are we able to fit 100 billion? How are we able to fit 5 billion of something on a tiny little chip? Well, the answer to that is we build them incredibly small, right? So here's actually this is a picture of a fairly modern transistor. I'm not going to go through all the pieces of it, but what I would like to call your attention to is the scale at the right-hand corner there, the lower right-hand corner, 30 nanometers. Okay, that's really small. It's hard to get your head around just how small that is because you think, oh yeah, sure, that's 3 times bigger than 10 nanometers. But we don't really have something for a sense of nanometers. It's just too small. But just as a point of reference, the wavelength of visible light, of blue light, is it's in the range of 400 something nanometers. That means, at this scale, light is just a wave. You can't even see this under an optical microscope. It's too small to be seen. That's how small this is. It's incredibly small, amazingly small. But I think you still can't get a good sense of it. In fact, even I, someone who does this every day, including holidays and weekends, thinking about this type of stuff, even I cannot really comprehend exactly how small these things are. But I find this nice experiment. Let's imagine that each transistor in the chip that you're designing is actually the size of a penny. How big would the processor be? Well, that's what 1,000 transistors looks like. Okay, then we have 100,000, 1,000,000 transistors, 10 million transistors. Remember, these are all pennies. 100 million transistors, 1 billion transistors. Okay, that's what a billion pennies looks like. Okay, that's how many transistors fit in one chip inside your cell phone. Remember that little piece in there? All those are jammed in there. Okay, each one of those blocks, by the way, is about 11 feet high, 41 feet by 45 feet. Each one of those boxes there is about the size of a large school bus. Okay, and all those transistors, that's 1 billion. 4 billion transistors fit in that little square. I can't even. I can't even. I don't understand how that's possible, but it is. Okay? It's amazing. The computational power that you have in a modern machine is just hard to comprehend. Okay, not only that, as I told you, actually, in a microprocessor, sure, I can build a lot of transistors, but how I actually wire them up actually gives them their structure, it makes the processor what it is. It gives it its computational abilities. So how much wiring do you think is in a little microprocessor? So here's actually a microprocessor. If you cut it in half, here's your microprocessor, you cut it in half, and then you look at the side. Actually, what you'll see is tons and tons and tons of these tiny, tiny little wires. Okay, and you can see the scale there. It's about 54 nanometers pitch between the wires. Okay, so here's kind of an interesting question. What if you took all those wires, okay, all the wires in that little tiny square that is your microprocessor, and you pulled them out with nanoscopic tweezers? It's a very hard job. Okay, you pull them all out and you line them up end to end. How long do you think how long do you think that wire would be if I just started pulling on it? If I start pulling on that wire, how much wiring do you think is in that tiny little microprocessor? As I start pulling, you would definitely be able to see it. It's long enough you can see it. In fact, I can get all the way across the stage. In fact, I can cross the stage. I can keep pulling all the way across to the other end of campus. In fact, I could keep pulling and walk all the way to the middle of downtown Santa Barbara from here. There's about 9 miles of wiring inside your little microprocessor. I don't know what to say. That's amazing that we build these things. So from here to downtown, easily. It's actually a little bit longer than that, probably about 9.5 miles from my calculations last night. Okay, not only do we fit a ton of these, billions of these transistors, and not only do we fit miles and miles of wiring into each microprocessor, we then actually run them incredibly fast. So for example, who wins this race? Light traveling a foot from here, that's how far you get. That's how far light gets to run, versus multiplying 200 numbers. I wouldn't put this up if light won, actually. The processor wins. In fact, not only does it win, it wins pretty handedly. In fact, it could do 200 and then you go for a victory lap of another 200 multiplies, right? That's how fast these things are. And I want to keep in mind, that's one microprocessor, okay? Then we take these one microprocessors and then we make giant warehouses full of them, right? So just thousands and thousands of CPUs fill data centers now, and they just go on forever. Amazing, amazing. Think about that. Think about the billions and billions of operations that are happening in each individual node there. And then the thousands or hundreds of thousands of cores that are actually spread across this whole data center. And think about the potential that you have in that computational framework. It's pretty amazing. So, big idea number 2, no one can comprehend the scale of computing that we do today. I do work in the data center, I do work designing tiny chips. I do this stuff, as I say, every single day of my life, and even I have to do this by math, because when I try to intuit it, I can't. You know, it's just the scale of this is too massive. Okay, so now the third big idea, I want to tell you about some research that we have going on in our lab. I've been lucky enough in my career to be able to contribute to the design of these microprocessors. But recently we've been doing a bunch of work that's trying to examine, how do we get even better? How do we get beyond some of the traditional limitations when we design microprocessors? Okay, and that brings us back to this picture of the switch. Now a switch, switch has this following property, which I didn't tell you about before. When I switch it, there's a delay between, when I close the switch and how long it takes for that left-hand side to propagate over to the right-hand side. Okay, there's a delay there. And in fact, that delay is one of the limiting things. That's basically what determines how fast you can run your microprocessor, is that delay. They add up. So, working with Professor Dmitry Strukov and one of his graduate students at Wyatt, we had a very interesting question, which was, what if we could use delay to do computation? Right? Rather than have delay be something that limits us, maybe we could actually do useful work with delay. It's kind of an interesting high-level question. And it turns out that, in fact, you can. In fact, what you can do is you can encode data that you want to do computations on as delay. And then some really interesting things happen when you do that. Okay? So here's a picture that kind of describes at a very high level. Now we're getting down into the details a little bit. But here's a picture that kind of describes the intuition behind this. If you have a signal, and those signals go from 0 to 1, it's still a binary system, just like a normal computer, where all the signals in the system are zeros and ones. And then time is running along the x-axis here. You can see a signal starts as 0 and then goes to 1. And I have 2 signals here, A and B, the top and bottom ones. Okay? Now what happens is, look, if I make a thing that basically takes whichever one arrives first, that actually is a logic gate, is a OR gate. But in this weird delay world is actually a min operation. If I take the thing that happens first, it's actually the min of A and B. And so that's actually really interesting. This is a kind of a neat observation, because I could take this very simple thing, a little tiny gate that I can build out of, on the order of 3 or 4 transistors, and I can do a new operation with them I couldn't do before. I can do this min operation. And you think, okay, well, min is nice, but you can actually not just build min, you can build a lot of different stuff. You can build min, and you can build max, and you can build median, and you can build increment, equality check. You can build all kinds of really interesting new functions in this weird encoding where delay is capturing how long, capturing the data you want to compute on. So we actually, did some really kind of theoretical work on this, and then we actually showed, oh, you know what, not only is it just theoretical, you can actually solve some interesting problems. And here I'll give you the intuition for one of the problems you could solve. One of the problems that works really well with this is actually if I want to find the shortest path. So I'm traveling from here down to Santa Barbara because I've got this tiny wire. I have to carry it down there. And I want to find the shortest path, right? Well, I can actually build a graph, this data structure, and I can actually say, look, what I want to do is I actually want to find the minimum path through this set of nodes. And in fact, these min and max and add, that's actually totally sufficient for you to do this type of computation. So you can do this kind of computation with a radical efficiency that you couldn't achieve before. And you think, shortest path is pretty nice. I like shortest path, but how often do I have to calculate shortest path? Actually, not all that often. It's not actually that hard of a problem either. But we also figured out, once we figured out that one, that you can do other more complex things. So one of the things that we figured out you could do is DNA sequencing. So DNA sequencing is actually kind of like shortest path, it turns out. It turns out that actually to find the minimum you have some DNA sequence here and some DNA sequence here, and you want to see how similar they are. What you're trying to do is actually match them up, and what you're trying to do is find the shortest path through this matching, really, and by doing so, you actually find the best matching between these two sequences. And we showed how actually using this very simple new type of computation that you can do this DNA sequencing very, very effectively. Then a really interesting thing happened. Okay, so we wrote this paper. It's still fairly theoretical. It's also still very application specific. We said, look, we're trying to solve this problem of DNA sequencing. We've been looking at some other algorithms. And we got an email from a researcher, Jim Smith, who was looking at the way the brain does computation. And he had a very interesting observation. He said, look, I believe, this is Jim Smith talking, that the brain actually is using delay to do computation. Because these neurons are actually connected up in all kinds of interesting ways that you can't explain any other way, and is his take. And that in fact, as the signals propagate through these complex networks in the brain, that actually in doing that, you're actually doing some computation. And we actually spent about 6 months trying to figure out how his theory and our theory actually connected, and it turns out they're actually deeply connected. And it turns out that you can sort of unify these under a single new theory, of which we call space-time computing, and basically it comes down to 4 basic operations: min, max, this delay, and this thing that's called inhibit, which basically allows you to observe something and then stop something in the future from happening. And we have some really nice new evidence that shows that, in fact, we believe this set to be complete. We believe that anything you can compute in this way can be computed by these 4 things. And we actually also know that these 4 things, you can implement them incredibly efficiently. So it's really exciting. So will it work? I actually don't know. There you go. But I know we built a chip. Actually, I had Wyatt build the chip, and I advised. One of the nice things about being an advisor. There's the first test chip that's doing this sort of delay propagation logic. It's pretty neat. So the story is out. Actually, I wanted to present to you something that's right at the edge of what we're doing today. We don't know exactly how well this is going to work. We don't know exactly what types of computations you can do more efficiently this way. We do have some strong hints that this is a really interesting new way to do computation, but we won't know until we actually take some applications that show that, yes, you can really do computation in this totally new way. But we're building stuff. So, number 3, my big idea 3, I think. We must continue to improve. We need to continue this trend of taking truly fantastical ideas and then turning them into mundane ideas through computation. I really deeply believe that. I also deeply believe from my work that I present here and many of the other projects I've done that we still have a long way to go. I know we can do much better, and we have a huge opportunity to make computing even better than it has been in the past. So I just want to thank all of my current grad students as well as my many past grad students who've worked on this project, and I'm happy to take any questions. Thank you.